Okay, hello everybody. I think we're ready to start. So good evening, good afternoon, and good morning to you all, depending on where you are in the world. It is really wonderful to see so many of you here with us today, even virtually. We have over 120 participants so far, and more will be trickling in. My name is Katerina Michaelides, and together with my colleague Raphael Rosalem, we are the leads for the water theme of the Cabot Institute for the Environment at the University of Bristol, and we are hosting this event today. So today is World Water Day, held on the 22nd of March every year since 1993. It is a day designated by the United Nations to celebrate water and to raise awareness of the global water crisis, of the 2.2 billion people living without access to safe water. The theme of World Water Day this year is valuing water, but thinking about value of water more than just its price or economic significance. Water has enormous value for our households, our food, culture, health, education, religion and spirituality, and the sustainability of our environment. And in order to manage this invaluable resource sustainably into the future, we need to understand and account for water's true multidimensional value for all societies across the globe. Here at Cabot Institute, we have chosen to focus our World Water Day event on hidden water, valuing water that we cannot see. We have invited two fantastic speakers who research different aspects of hidden water: groundwater buried deep underground and glaciers that lock up water as ice. I'm a big fan of both of these women, not only because of their interesting science, but also because of their passion and talent for communicating science to a broad audience. The way the event will work is that both talks will run back to back, each lasting around 25 minutes. And at the end of both talks, we will open it up to questions from you guys, the audience, for around 15 to 20 minutes. You will be entering your questions in the Q&A chat button at the bottom of your screens. And my colleague Raphael will chair that second half of the event. Okay, so let's get started. Our first invited speaker, Debra, if you could turn on your camera, is Dr. Debra Perrone. Debra is an assistant professor at the University of California, Santa Barbara's Environmental Studies program. Debra's research focuses on groundwater resources and the challenges facing their sustainability under climatic and anthropogenic pressures. She combines various methods from across engineering, physical science, policy science, and law to inform water sustainability and public policy. Her research is shared through policy briefs, interactive online dashboards, and publications in the top scientific journals. Debra is a rising star among a new generation of hydrologists, and we're particularly excited to have her with us today. Debra, over to you.
Thank you. Thank you so much for that introduction, Katerina. I'm thrilled to be here today at the Cabot Institute to celebrate World Water Day, a day where we can acknowledge the value of having access to fresh water, and a day where we can highlight our biggest water challenges to inspire solutions. A special thank you to Katerina and Raphael for the invitation to speak to you all today, to Vicky for organizing the webinar, and to Jemma for highlighting another hidden but vital water resource, glaciers. Today, I'm going to tell you the story about groundwater. Groundwater is an overlooked resource. It's often referred to as the invisible resource hidden beneath our feet. While groundwater may be hidden beneath our feet, when it comes to the surface, it provides more than half of our global population with drinking water. And it provides about 40% of the water used for irrigated agriculture globally. This map here shows irrigated area serviced by groundwater, and there's a few countries that really pop out on this map: China, India, and the United States. And today I'm going to begin my story with the United States and then move to a more global context. So there's no doubt that groundwater is an important resource. There's also no doubt that we are overusing groundwater in many places throughout the United States, which is leading to depletion. There are many undesirable results from groundwater depletion, such as land subsidence or saltwater intrusion, and many of these have been studied extensively. One manifestation of groundwater depletion that has had little attention beyond the media, such as examples that you're seeing here on the screen, is when groundwater wells run dry. So what does it mean when a groundwater well runs dry? Well, it means that water levels decline so significantly that it's no longer possible to pump water up to the surface. But until recently, it was hard to know where wells were vulnerable to running dry because well drilling is rarely studied. Until our recent report, we didn't know where groundwater wells were constructed, the depths to which they were constructed, or the reasons for which they were constructed. One reason for this is because water quantity is mostly the matter of state law in the United States. So each state has its own unique guidelines for collecting and sharing these data. This map highlights some of the reporting biases that we encountered when collecting these data. Now, it's not that states lack information about groundwater wells. It's for the most part, state and sub-state information has not been stitched together. So we collected and collated and quality controlled groundwater well reports that have well construction data for each of the United States. This took us 5 years, but I think it paid off. For example, well reports show us where groundwater wells are constructed and used. So here we show 11.8 million groundwater wells, with each one of the dots on this map marking one groundwater well constructed and recorded between 1950 and 2015. If we categorize all wells into 3 broad categories, we find that 83% of reports indicate a well was constructed for domestic or municipal purposes, 15% for irrigated agriculture, and 2% for industry. Here we see the depths to which wells are constructed, and this really provides a lens into the subsurface. Light blue here indicates shallow wells, dark blue indicates deeper wells. The average depth of a well is 60 meters, which is equivalent to the height of a 4-story house. The median depth is 44 meters, and this is equivalent to a 3-story house. Now, while some of the patterns you are seeing here are the result of data collection biases across jurisdictional boundaries, such as the one that I point out here, many of the patterns that we're seeing are actually really important patterns to give us insight into what's happening underneath the ground. So in light purple, fading in now, you will see the overlap between groundwater well depth and major US aquifers. Before this map, most of our understanding of how deep or where people were drilling groundwater wells was based on local anecdotal information. This is the first time this information has been stitched together across state boundaries. So we used this information about groundwater well depths to compare local water tables to find out where groundwater wells ran dry during the most recent drought. We found that 1 in 30 groundwater wells were dry in the western 17 states. These dry wells were often clustered in rural areas like the one you see in this footage. Dry wells really leave households to bear the brunt of the impacts from declining water levels. Rural areas are isolated from urban infrastructure, so households tend to rely on access to water from private wells, rather than from a connection to a public supply system. Because water is so intertwined with livelihoods, I found that the impact of a groundwater well running dry comes through best when we hear about it from those who are living this reality.
Now is a lot of the homes, the majority of the homes, have their own private well system, which feeds water to their home. And those wells are all drying up.
It is absolutely an emergency. Tulare County is really ground zero for the drought in California. Approximately 55 to 60% of the dry wells in California are in Tulare County, with the majority of those wells being in this specific area of East Porterville.
Unless it directly affects you or someone you love, you don't understand what these people are going through.
So this video is from the peak of the drought in California. And just to give some context here, we're in one of the richest countries in the world. We're in California, a state by some accounts is within today's top 10 economies in the world. And yet there are people in multiple communities without access to safe, fresh drinking water at their homes. So what can we do when the well runs dry? Well, one opportunity is to drill a deeper well. So we asked the question, are people drilling deeper wells over time? In addition to information about the location and the depth of wells, groundwater well reports also provide temporal information about when groundwater wells were constructed. We could use this information to plot time series of depth trends. Here's an example near Stockton, California. Across the x-axis, we have time. Across the y-axis, we have depth in meters below the land surface. And each circle on this plot represents one groundwater well construction event, such that this groundwater well was constructed in the year 2000 at a depth of 100 meters below the land surface. We could do this same analysis for areas with at least 100 groundwater wells. This map shows rank correlations of time versus well depth for the years 2000 to 2015. The areas in gray indicate little to no trend. The areas in blue indicate that newer wells are shallower than older wells, and the areas in orange and red indicate that newer wells are deeper than older wells. The white states here indicate that we didn't have enough data to run statistical analyses. Even with just a quick look at this map, we could see that there's more orange and red than blue. Looking across all time periods, we find that it's 1.4 to 10 times more common for newer wells to be deeper than older wells. So we know that people are drilling deeper groundwater wells, but the question remains, are people drilling deeper wells where we have declining water levels, which would reduce their vulnerability to groundwater depletion? So we paired two data sets, groundwater well reports, which give us information about groundwater well depths over time, and monitoring wells, which give us groundwater level information over time. This information can allow us to better understand the relationships between declining water levels and well depths. On the right-hand side, you see a satellite image. The blue dot here is a monitoring well where groundwater levels are measured. The yellow dots are constructed groundwater wells within a 5-kilometer buffer. Here we picked a 5-kilometer buffer as a Goldilocks approach. We wanted something that was big enough that would allow us to take statistical samples of wells, but we also wanted something that was small enough that we could understand and capture the local subsurface heterogeneity. So let's go back to Stockton, California. The blue area here shows the water level time series. Over the period of interest, the water levels declined at a rate of 3 meters per decade. The yellow circles show the constructed groundwater wells within a 5-kilometer buffer of the monitoring well. And over the period of interest, groundwater wells were constructed deeper at a rate of 7 meters per decade. So folks in this area are drilling deeper at a rate that is more than twice the rate of water level declines. These patterns could be revealing risk aversion or worry that groundwater levels will continue to decline into the future. So if we look at the lithology in this area, which is also provided by the groundwater well reports, what we see is that in this area, we have a thick, mainly sandy aquifer. This is a subsurface profile that really supports deeper drilling. We can translate the local scale information, like we just explored for Stockton, onto a plot that helps us understand trends at a regional level. Across the x-axis, we have well completion depth. Anything that plots on the left side indicates a shallowing trend. Anything that plots on the right side indicates a deepening trend. Across the y-axis, we have the water level trend. Anything that plots across the top indicates a rising water level. Anything that plots across the bottom indicates a declining water level. So for Stockton, the well depths are getting deeper over time. You see this with the yellow dots. They're getting farther away from the land surface. So we would expect to be on the right-hand side. And the water levels are declining. You could see that with the blue area, where we see a declining water level over time. And so we would expect to be across the bottom two quadrants. So for Stockton, we end up in that overlapping quadrant on the lower right. So if we zoom out, we can perform the same analysis for the entire northern Central Valley. On the left-hand side here, we see a zoomed out satellite image. Once again, those blue dots indicate monitoring wells, and the yellow circles show the corresponding buffers. In the Northern Central Valley, also known as the Sacramento Valley, 83% of sites fall in that bottom right-hand corner, where a site is a monitoring well with water levels between 2000 and 2015, and its nearby groundwater wells constructed during the same period. So what does this mean? The majority of monitoring wells in this area are showing declining water levels, while people in the surrounding area are drilling deeper wells over time. So we can perform these same analyses for aquifers across the United States. Today, I'm going to focus on the Central Valley and the High Plains. The different colors here correspond to the portion of the aquifer underlying each state. This is important because we know that each state collects data differently. Why did I pick the Central Valley and the High Plains? Well, the Central Valley provides 1/4 of the United States food. It's also very well known for its production of fruits such as strawberries and nuts such as almonds. The High Plains supports 1/6 of the world's grain production, and so it's also a critical aquifer known globally. So looking at each of the regions of the Central Valley, we see consistent patterns. Most sites fall in that lower right quadrant. This is suggesting similar patterns to what we've seen in Stockton. We have declining water levels and deeper wells. With a thick alluvial aquifer that supports deeper drilling, this is not surprising. In fact, in this area, limits to drilling are less of a factor of the hydrogeology, so what the subsurface looks like, and more of a factor of economics. This is really highlighting the haves and the have-nots. In order to drill a deeper groundwater well, you tend to need tens of thousands of dollars for a household well or hundreds of thousands of dollars for an agricultural well. So now if we move eastward to the High Plains, the first thing that pops out here is that we have a lot less clustering in that lower right-hand quadrant like we saw throughout the Central Valley. While the northern and central High Plains have interesting trends, I want to draw your eyes to the southern High Plains. Here, we see that the dots are mostly spread across the bottom two quadrants, indicating that declining water levels are indicating we have declining water levels, but also indicating that declining water levels are not always being met by deeper drilling. In the southern High Plains, we see that although monitoring wells indicate declining water levels, well depth trends are both shallowing and deepening. Sure enough, if we look at the lithology, we see that folks are hitting a low permeability layer that's above high salinity groundwater. Unlike the Central Valley, the hydrogeology and the water quality of this area are limiting the extent of deeper drilling. So what's the big take-home message? Declining water levels are not always met by deeper drilling. This is implying that shallower wells may be more vulnerable to drying up should depletion continue in this area. Now, there's a number of factors that can lead groundwater users to construct deeper wells over time. Better technology. We can drill deeper today than we've ever been able to do before. Shallow pollution. People could be drilling deeper to avoid shallow contamination. Regulation. We are finding that some aquifers are exempt from requirements, incentivizing people to drill into deeper aquifers that are not regulated. And water quantity. In search for higher yields, people could be drilling deeper groundwater wells. They could also be trying to regain access to groundwater after their well runs dry. This latter reason has been especially salient for people in California and across the Western United States. Regardless of the factors, the question remains, is drilling deeper a solution or a stopgap to groundwater depletion? We suggest that drilling deeper is a stopgap for 4 reasons. First, groundwater wells are expensive. Domestic wells can cost tens of thousands of dollars, agricultural wells can cost hundreds of thousands of dollars, and a new municipal well can be more than $1 million. People don't have the money to drill the new wells, and that's the biggest problem. This is a quote from Jim Smith, whose well ran dry because the groundwater level declines during the most recent drought in California in the late 2010s. Reason 2, low permeability rock formations. At some point, groundwater users hit a bottom like we saw in eastern New Mexico. What does this mean? They can't go deeper. What we know is that the edges of the southern high plains are characterized by a really thin, saturated thickness, which is defined by the offset between the bedrock and the water table. This map here shows the difference between well bottoms in the high plains aquifer and the base of the aquifer. Here, the red dots, which are, which range from the southern to the northern high plains, indicate that wells have a bottom less than 20 meters from the base of the aquifer. So this is a quote from a review of water supply options for Portales, New Mexico, a city in the southern high plains. Deep groundwater is of low quality and likely also of low quantity. In this area, folks hit that low permeability layer, and underneath that is brackish water, which leads us to the third reason. We tend to get brackish water with depth. Groundwater tends to get saltier as we go deeper, so it may not be feasible to use this water without desalination. Reason number 4, increased energy requirements. Energy requirements increase with every foot water is lifted, and our data suggests that deeper wells tend to have deeper water levels. In areas where pumps are powered by high carbon energy sources, the combination of declining water levels and deeper wells could increase CO2 emissions per unit of water pumped. In conclusion, deeper well drilling is a short-term solution to groundwater depletion. This conclusion is intuitive, but it helps to have 12 million groundwater wells to show these patterns at the continental scale. The reason for this is because each well and each aquifer tells its own story, weaving together the heterogeneity of the subsurface and the heterogeneity of the actions of groundwater users. The challenges that we've just explored are not constrained to the United States. Groundwater is the most mined substance in the world. We abstract 200 times more water than oil from the subsurface. So we started collecting well data across the globe to advance our understanding of local well vulnerability to groundwater depletion. These plots show groundwater well depth in meters below the land surface. The light purple pink is showing shallow wells, and the dark blue is showing deeper wells. Like in the United States, we are seeing really interesting geospatial trends that tend to align with local subsurface conditions. We use this information to compare the depths of wells and water tables to identify wells that are running dry, and also wells that are vulnerable to running dry should groundwater levels continue to decline. The plot that we're seeing here, across the x-axis, we have frequency, and across the y-axis, we have well depth in meters below the land surface. Anything that plots with a negative value suggests that the well bottom is above the water table. This suggests that we have a dry well. Anything that plots with a positive value indicates that the well bottom is saturated with water. We found that 1 in 30 wells globally were shallower than their nearby water table. We also found that an additional 1 in 30 wells were within 5 meters of their nearby water table. This is suggesting that maintaining groundwater levels can protect millions of wells from running dry. Now, I really see this as an opportunity, and this is the inspiration behind some of my other work looking at regulatory solutions in the United States, which can help folks adapt or move towards sustainability. I'm doing this through what we call the Western Water Dashboard. The Western Water Dashboard is an online interactive website that allows stakeholders to review different regulations to pumping groundwater. The focus here is on permitting or getting permission to pump groundwater prior to use. So this is what groundwater pumping looks without permitting. So you construct your groundwater well, and then you put that water to beneficial use. New pumping with permitting has this extra step, And permitting allows water managers to consider things like water budgets and other aspects of valuing water, like people's wells going dry or having access to water for all at their household. This research really leaves me feeling optimistic. Our preliminary findings suggest that there is this movement to control new pumping, even in the Wild West. This makes me optimistic because we have signals of proactive management, and what we're seeing is that there's laws that provide powers to water managers to consider things like equity, like people losing access to drinking water at their household. Slowly but surely, I believe we are making the invisible visible. Thank you.
Thank you so much, Deborah. That was a super talk. So many interesting things in there to pick up on later. So we'll have to move swiftly on. Thank you. So our next invited speaker is Professor Jemma Wadham. Jemma is Professor of Glaciology and Director of the Cabot Institute for the Environment at the University of Bristol. She also holds an adjunct professorship at the Arctic University of Norway. She has led more than 25 expeditions to glaciers around the world, including to Greenland, Antarctica, Svalbard, Chilean Patagonia, the Peruvian Andes, and the Himalaya, and has won several prestigious national awards for her research. Jemma is a pioneer in the field of understanding glacier-hosted life and the impacts of glaciers on our global carbon cycle. We're particularly thrilled that she's joining us today to share her research. Jemma, over to you. You're muted, Jemma, sorry.
Right. Hi, everyone. Great to see so many of you here today. Thanks, Katerina and Raphael, for this wonderful opportunity to talk about our valuable water. I'm going to take you now on a journey to the peaks of our planet, where we have a very precious water resource in the form of glaciers. And I'm going to talk particularly about glaciers in the high Peruvian Andes. The project I'm going to talk about is some preliminary findings from a project called Cascading, which is jointly funded from the UK and Peru. It's very interdisciplinary. It brings teams together between the UK and Peru, and with a principal investigator, Raul Loaiza-Muro, in Lima. And essentially what I'm going to talk about today has three different parts to it. So I'm going to talk firstly about our hidden glacier water and why that's important. I'm then going to talk about water quality and what I'm calling the water quality time bomb in this particular region of Peru. And then thinking beyond the problem about how we can start to find solutions to these problems of water quality in rapidly retreating glacier regions around the world. So glaciers are really important as water stores to us. They actually contain over 2/3 of the world's fresh water. It's a phenomenal amount of water locked up in ice and snow. Most of that is in Antarctica and Greenland. But actually, if you look at the mid-latitudes and the tropics, you've got some very extensive areas of high mountain ice in the Himalayas and in the Andes and a few other places as well, which are really important as water resources for millions of people that live in quite challenging conditions in the mountains. Today, I'm going to focus on a particular mountain range in the western part of Peru called the Cordillera Blanca. You can see it just labeled there. It's not far from the coast. If you want to get there, you have to arrive in Lima and then jump in a car or a truck and drive for about a whole day along the coast and then up into the mountains. And the Cordillera Blanca is actually the world's most extensive tropical mountain range. And it kind of includes about 1/4 of the tropical glaciers of the world. And these glaciers, they're in the tropics, but they survive by sticking very, very high up at altitude, normally above 4,000 meters above sea level. That's higher, higher than something like Mont Blanc. And you can see some pictures there of some just high tropical mountain glaciers. Unfortunately, just like in many mountain regions of the world, the air temperatures are warming at rates which are higher than the global average in this region. And that creates a challenge for these particular glaciers, as it does in many mountain regions, the Himalayas, the Alps, parts of the Arctic as well, and the US and beyond. If we just want to look at these glaciers and see what they might look like, this is Huascarán, the highest peak in Peru, and you can see some glaciers here kind of tumbling down the mountainside. and sort of 6,700 meters above sea level. These are high altitude places and quite difficult to work actually as a field scientist. We got some more traditional valley glaciers here, again, very, very high up in the Peruvian Andes, tumbling down the mountains over quite steep slopes. And what's quite interesting about these glaciers, I've only been working on them for the last couple of years, and I normally work on glaciers where there's a winter and a summer. And what's different about the tropics and the tropical glaciers in Peru is that you have a rainy season and a dry season. So air temperatures are fairly constant throughout the year, but you have a rainy season where you have maybe 80% of your precipitation falling, which peaks in around February, March. And then you have a dry season where there's very little precipitation at all. And that peaks around sort of July, August time. And that means that these glaciers are melting all year round on their lower tongues. That makes them very sensitive to any warming, and they're nourished by snow during the rainy season. They're very sensitive to the freezing level, as you can imagine, as if we warm climate and the freezing level goes up, you can turn areas of the glacier that weren't previously melting to suddenly melting. So there's a high sensitivity here by these tropical glaciers to kind of global climate change. This is what they look like. This is Pastoruri Glacier, a picture taken in the dry season. You can see the clear skies, blue sky in the background there, kind of gleaming, melting ice surface, bare ice in that case in the dry season. If you go back in the rainy season, it's a very different story, cloudy skies, much more frequent precipitation. And you can see a very thin blanket of snow over the surface of that glacier there. That blanket of snow is really important. Firstly, it's very reflective, so it reflects radiation back to space and prevents that glacier ice warming up too much. And it also nourishes the glacier by providing, extra snowfall that helps it keep in healthy balance. All year round, you have water coming off these glaciers. And so this is a little subglacial portal at the front of Pastoruri Glacier, where you can see water coming out and flowing down slope. Glacier change, as I've been saying, has been dramatic in this region. So we have some pictures here of Pastoruri from the 80s until 2016. And you can see the dramatic shrinkage of what was a single bulk of ice to some fairly small blobs some decades later. And actually the whole glacier is split into two in this case. So over the region, we've lost about 30% of the area of glaciers. That's fairly phenomenal. And that shrinkage will continue by the end of the 21st century. And so these glaciers, they're sensitive. They're almost what you could call the canary in the gold mine. They're responding quickly to global warming, and that's going to continue as we go forward over the coming decades. This is the region we're working in. This is Cordillera Blanca. You can see it just trending diagonally across the screen there. The blue line is the Rio Santa. That's the major river of the region that takes water from the highlands in the south, sort of northwest, and then eventually into the Pacific. You can see the tiny little white blobs. Those are the glaciers of the Cordillera Blanca, and they're very important in feeding water supply to that river, particularly in the dry season. We drove from north to south along that river base and sampled quite a number of tributaries along its length, which I'll talk about a little bit later. What's really important about these glaciers in this particular region is that they store up water during the rainy season, and then they release it in the dry season. So you can see here's a graph of through the year of a catchment, of a river catchment, which has very little glacier cover. And the dotted line is rainfall and the hard line is discharge. You can see pretty much they follow each other. If you go to a catchment in the same region, which has got 30% glacier cover, there's a difference. So the rainfall goes up and then it goes down. But during the rainy season, you have depressed water in the river simply because a lot of that precipitation is being stored as snow on the glaciers. But then when we get to the dry season, when the flow is low in the rivers because the rains have stopped, the glaciers can help out by providing extra water. So they smooth out that kind of delivery of water to settlements throughout the year, which is really important. So for the Rio Santa, almost half of its water in the dry season is glacier melt. And this is a region of very high water demand. There's about a quarter of a million people in Huaraz, which is the main town. And so these rivers, these glaciers, are really important to water supply in that region, which is why their shrinkage will impact that flow of water throughout the year, but particularly during the dry season. The only thing is, we've often focused on water quantity rather than quality. I'm actually a water chemist, so I mostly look at water quality. And in this region, you can't help but study the quality of the water. This is a picture of water coming out of the front of a glacier called Shayap in the Cordillera Blanca. The acidity, the pH of that water is about pH 2 to 3. It's about the same acidity as your stomach. It's also very concentrated in toxic metals, things like lead and iron and manganese. And you can see the orange color around its edges. That's essentially iron falling out of the water, precipitating it and to form what is commonly known as rust. As you go further downstream, this is the lake in front of Shayap Glacier. It's bright green. Again, that's because of the high concentration of metals. So you have a looming water quality problem in this region, which quite a number of people have already kind of discovered. And the question is, what's going to happen in the future, and why is this happening, and what's it got to do with glaciers? And to kind of explore that, I'm going to go through a kind of a series of layers that help explain the problem, starting off with rocks. So the rocks of the Cordillera Blanca, basically this whole region sits on a plate boundary where the Nazca plate dies beneath the South American plate, and some 8 million years ago, molten low density rock rose to the surface in this red blob here and pushed up former sediments, so marine rocks, marine sediments. As it did so, eventually it cools and it pushes up those sediments, and then what we've got is this batholith, which is basically a solid lump of what was molten magma. And you've got the younger sediments, the sediments which are green and brown here, pushed up, and they're sort of sitting on top of this batholith. And then because it's quite high up, glaciers have then formed on the top. So you kind of got this layer cake of batholith, sedimentary rocks, glaciers. And the sedimentary rocks is one particular type called the Chicama Formation, which used to be at the bottom of the ocean, and it's full of metal sulfides, which is the key fact here. If you look at the geological map of the region, you can see that. So the red is the batholith I was just telling you about, which is mostly sort of granodiorite, very hard silicate rock. On top of that, you've got this Chicama Formation, which is formed from the Jurassic, so 150 million years ago or so, which is the blue. And then the light blue is the glacier sitting right on top of that kind of layer cake of rocks. And you can see that in photos. So you can see these rusty rocks right around the edge of the Shayap Glacier here. That is the Chicama rocks. And here's a close-up picture of them there. You can see that iron coming out of the rocks and oxidizing in the air. And it's really important to think about, well, why is this happening near glaciers? And I'm going to try and explain why we think that might be now. So firstly, glaciers are a bit like natural mines. They move over their landscapes, they grind up the rock beneath them into quite fine powder. Actually, you can see that in this picture here, some little dishes of sediment that's come out from the bottom of the glacier in the water. Actually, this is in the Himalayas. It's a different color to what you might see in Peru, but you can see it's very fine. It's sand, it's silt, very high surface area. And as the glaciers grind up their rock, what they do is they release reactive minerals in that rock that would normally be kind of caught up in the lattice of the rock. And two particular minerals, which are very reactive, tend to get released beneath glaciers during this crushing process. On the left here, we've got pyrite, so often known as fool's gold. It's a shiny mineral. It's called pyrite after the Greek for fire, pyre, and that actually used to be used by early humans to create fire, actually by bashing flints together because it creates sparks. Very, very reactive. On the right-hand side here, we've got carbonate. So this is the stuff you find in your kettle. It's sort of like lime scale, really, calcium carbonate. And basically there's a battle between these two very reactive minerals that get released when the glaciers erode their bedrock. So the pyrite oxidizes and it produces acid, iron, and an ion called sulfate. That's the equation on the top here. And the carbonate can then neutralize that acidity because the acidity attacks the carbonate and it releases calcium into the waters. So it's a little bit like in your kettle when you might put some vinegar in your kettle to dissolve the limescale. Vinegar is an acid, it dissolves the calcium carbonate in your kettle. So essentially it's the same thing going on here. These two rocks in combat. you know, an example you might see on buildings of this sort of thing going on. Back in the days when we had acid rain in quite a difficult times, you know, on the left you've got a gargoyle or a grotesque where the acid hasn't done a particularly good job of attacking the rock yet. Rock is winning. On the right, the acid's winning. You know, the calcium carbonate of the rock face has kind of dissolved. And the thing is, I'll introduce you to 3 glaciers that I'm going to talk about. First glacier is a glacier called Cohup, the Cohup Valley. You can see beautiful, pristine environment. The rocks in the foreground here are the batholith rocks, so they are, you know, not rusty red. They're a nice grey colour. This catchment is a happy catchment. Its waters are alkaline, not too high concentrations of toxic metals. It's doing well. If we go to its neighbour, the Shiap Glacier, you can see a dramatically different picture. You can see rusty rocks, these Chicama formation rocks all down the sides. The rivers are acidic, the lake's acidic, the waters are very toxic in terms of their metal concentrations. And this is a catchment that isn't doing so well. Another glacier I'm going to talk about is called Pastoruri, which we saw earlier, has retreated dramatically over the last few decades. Again, it has some of these Chicama rusty rocks around its margins, and its waters are acidic and toxic coming out the front. What's interesting for me is that actually I've studied quite a lot of glaciers over the last few decades. And here are some pictures of my glaciers. And you can start to explain why these glaciers in Peru are having such a hard time, or why their rivers are having such a hard time. So what we have here is some glaciers that I've studied, or various other colleagues have studied, that sit on soft sedimentary rocks, a little bit like the Pastoruri and Shiap Glacier in Peru, which sit on these Chicama rocks, soft rocks from that used to be in the bottom of the oceans. On the right here, we've got these green colored glaciers, which are things like Greenland, Patagonia, the Himalayas, Norway, and also our Cohup Glacier, which was the healthy river catchments. And these glaciers all sit on, you know, igneous metamorphic rocks, hard rocks, very difficult to erode, not so reactive. And then what we can do here is we can look at the sulfate concentrations produced by this process of the sulfides oxidizing in the bedrock, and that's sulfate going into the waters. We can plot that against the amount of sulfur in the sediments from these glaciers. And that's the amount of sulfur directly relates to how much of these nasty iron sulfide minerals we have, which are creating the acidity and creating the metal toxicity. And you can see here, most of these glaciers, including our happy, healthy glacier Cohup in Peru, they sit right down the bottom of this diagram. So their sulfur concentrations or their sulfide concentrations are not too high, and their sulfate concentrations are also, you know, relatively moderate. If we look at our Pastoruri and Shiap Glacier, you can see they're off the chart. They've got very high concentrations of sulfur in their rocks and very high concentrations of sulfate. So you can see why these 2 glaciers might be having a problem, because we know that the same process that produces this sulfate from these oxidized sulfides also produces acidity. So the question is, does that acidity get neutralized by our carbonates? And here what we've got is, on the y-axis, we've got the neutralizing power of these glaciers or their rivers from carbonates, basically, which produces calcium and magnesium. And on the y-axis, on the x-axis, we've got sulfate, which is produced by our nasty process, which is the sulfide oxidation. And most of the glaciers or river catchments I've studied are alkaline, and they're plotting around here. So, you know, they've got some sulfate from our iron sulfates, but they've got quite a lot of calcium, magnesium. So the carbonates are neutralizing that acidity being produced by the sulfides. But Shiap and Pastoruri are right out here. Their waters are very acidic, similar to lemon juice or your stomach. You know, it's not great. And they're not really doing a very good job. So you can sort of see why they've become acidic. They've got very high amounts of sulfide in the bedrock and not really enough carbonate to actually neutralize that acidity. So you can start to explain it based on the geology. But what about the metals? So the same process that's producing that acidity is also producing iron that's coming out of those iron sulfides. You also have other metals tied up in those sulfides, so they're being released too. And here are our 3 glacier catchments again. We've got the red and the orange, which is Pastoruri and Shiap, our problem river catchments. And we've got Cohup, which is our more pristine, healthy river. And then we've got a bunch of metal elements down the bottom there, where we've compared the concentrations relative to the kind of USA maximum constant contaminant limit. So what you wouldn't want to drink is anything above this line of zero here. And you can see for sort of iron, lead, and manganese, certainly our catchments which have got problems, Pastoruri and Shiap, you've got the concentrations of metals which are higher than you'd like them to be, higher than you'd want to drink in the water. But Cohup, our alkaline catchment, is doing pretty well. So we've got this rock which is driving acidification, which is then driving high concentrations of metals being present in the water. We had a very nice trip from the north to the south of the Cordillera Blanca and sampled a number of different tributaries that drain into the Rio Santa to see how widespread is this acidification and metal toxification in the rivers. Is it something that's happening everywhere, or is it just these few small catchments that we've been focusing on? And this is just a plot of the pH, so a measure of the acidity of the waters. And anything that's orange, the orange circles indicates it's acidic. And so, Shiap and Pastoruri are in there. There's another one, which is the Rio Kilkai, which has been quite well studied actually by US colleagues. And they're the kind of the orange dots. Anything which is green is doing okay. I mean, it's just around about neutral, and anything that's blue is alkaline. So you can see it's not a widespread problem at the moment if you sample the waters low down in these tributaries. But the question is, will it get worse? When you look at the metal concentrations from those same set of rivers, you see the same things pretty much. So Shiap, our toxic river catchment, and Pastoruri, you see high concentrations of what we've got here: lead, manganese, and iron. Cohup, the concentrations are much lower, certainly within sort of drinking water standard limits. And our other rivers, which are labelled sort of 1 to 28 along the bottom here, are generally okay. So it's not a widespread problem at the moment, but the question is, as the glaciers retreat, is it going to become a widespread problem, particularly given the scarcity of water in the region and the importance of it to rivers, particularly in the dry season of the year? But why would glacier retreat make a difference? And this is where some of the research of our Peruvian colleagues have come in. So this is work by Bram Willems and Raul Luisa Moro's group, and their two students, Yzette and Jorge. And you can see here, this is just from Google Earth, but they're looking at whether you can detect this from space and what's happening from space. And you've got two lakes here. You've got a nice blue lake up the top left, and you've got a green lake down the bottom right. Now, the green lake is acidic and toxic. The blue lake isn't. You can also see some kind of orange colored rocks, which is this Chicama formation, the very sulfidic, sulfide-rich rocks. And what they've been trying to do is use satellite images so you can detect the spectral characteristics of the surface and map where you got the Chicama rocks and determine whether the lakes have gone acidic or not over the entire region, which is pretty phenomenal. And this is just a little graph of so their preliminary results that they're sharing. And you can see the blotched area where the Chicama formation, they're mapping it. You can see these lakes here, which are acidic. They're bright red in their spectral characterization. And this lake is alkaline, it's doing fine. But when they plot the area exposed of these Chicama rocks in front of the glaciers against the pH of the lakes that they're also able to infer from satellite imagery, they find that just about anything above about 60 hectares of Chicama, which is exposed in the catchments, the lakes seem to be acidic. So there seems to be a threshold whereby, as you have Chicama rocks exposed in areas of more than 60 hectares in a particular catchment, it seems to flip from being alkaline to acidic. And it's very likely that what happens is that as these rocks get exposed in the fall fields of the glaciers and the sulfide minerals are exposed as well, they're able to react much more quickly in the air, in the oxygenated air, compared to beneath the glacier, where we know there's much less oxygen around, and actually these processes happen a lot more slowly. So there's some really interesting things emerging here about what's causing this toxification. I'm just going to tell one quick story which relates to what we do about this problem. So going back to my third river catchment glacier, Perrone Glacier, which feeds the Pachacoto River. So if you remember, I said in the headwaters of this river catchment, the waters are very acidic. They're pH 3, pH 2, and there's quite high concentrations of metals. If you go 20 kilometers downstream to where the river drains into the Rio Santa, and this is Fiorella Lamata, one of our researchers in Peru, these waters are fine. They're reasonably alkaline. The concentrations of metals have gone down. So it looks like in this river valley, it recovers. And that's really interesting because it's the landscape is finding its own solution to a toxification problem. And the reason it does recover is if you look at the valley of Perrone and Pachacoto, you can see it's got this lovely broad flat bottom and these gently sloping moraines that would have been glacial deposits, you know, thousands of years ago. And groundwaters develop in those moraines, going a little bit back to what Debra was talking about as the importance of groundwaters. And these groundwaters are alkaline. This is where the batholith kind of exists in the lower parts of the valleys. And they feed alkaline springs into the main river that gradually help neutralize that acidity as it travels down to the Rio Santa. The second thing that these valleys have are these wide bottoms, broad bottoms of the valleys, and they have natural wetlands where the native Andean plants are actually able to cope with the amount of metals in the water, and it takes it out, they take it out of the water. They're helping purify the water, which is quite incredible. And so these are some of the reasons why that river recovers. So why doesn't our other river recover, the Chayap Glacier, which was also toxifying its catchment? And this is what that glacier valley looks like. And you can immediately see the different steep side walls where water is probably running off very quickly before it can become very alkaline and help neutralize the water in the main river. And also you can see it's a much more sort of V shape as a valley. And so you don't have the opportunity for extensive wetlands to build up in the bottom and help purify and filter out some of those toxic metals from the water. So you can start to see some natural processes in the environment which are helping solve the problem. Which brings us on to the third part of this talk, actually, which is what's the solution? And this is something that the Peruvians are focusing on, Raul's group in Lima, is to try and take some of these natural processes and implement them within the landscape to solve the problem for local communities. So it's acting in advance of there being a large-scale problem. So taking the Andean plants, taking bacteria that can oxidize iron from a dissolved phase to a kind of a rust, a kind of insoluble phase, and take it out of the water, and then develop these natural wetlands where you feed the water in and you feed it down a very tortuous flow path. And as it follows that flow path, it gets neutralized by lime, which they put into the wetland. The metals get taken out by the plants. And there's some work been going on also looking at bacteria and how they can actually help take out some of the metals or change them to forms which are less toxic. And we're working in collaboration with a number of communities in the Peruvian Andes to help them to develop these wetlands so that they can start to take control of their own water supply and remediate it and sort of actually be sort of empowered to kind of detoxify their own water supply. And the other thing Raul's group are doing it's easy for me or us to go out there with our fancy chemical instruments and look at, you know, how acidic the water is and how much metal is it. But actually for someone living in these regions, it's much more difficult. And so what Raul and Fiorella have been doing is using indicator species of water quality and using macro-invertebrates. So these tiny little creatures that live in the beds of rivers. And some of them are very acid tolerant. On the left here, we've got chironomids and a number of other organisms, and on the right we've got acid sensitive families, so things like caddis fly larvae, things you have in the UK as well actually. And actually if someone can see and identify what's in these waters, that can tell them how good they are to drink. And they've developed an app which can be used by someone to plug in what they see, and then the app will tell you how good the water quality is. So again, it's helping people figure out how to solve the problem, but also to identify whether they have a problem and when they have a problem. And so this community work has been really interesting, and this is the next part of our project actually. So just to put it all together, in terms of our world glacier water, I mean, the Peruvian Andes is an interesting situation, but it's a perfect example of cascading impacts, from starting off with a geological situation where you've got a particular rock type and particular minerals in the rock, to the fact you've got glaciers in the region which are modifying the rock. They're crushing up the rock, they're adding meltwater to the rock, and that's releasing particularly reactive elements of the rock, like these sulfides, which create the acidity. You've got natural processes in the environment that are helping take out that acidity, whether that's plants or kind of rock weathering reactions, and that determines how effective they are, determines what the water supply is to the local people and sort of biological organisms and plants in that region. And I guess what we don't know is what's going to happen in the future, but what we do know is that almost certainly these glaciers will continue to retreat. I think the most optimistic scenarios are that maybe half will be left at the end of the 21st century. So we may as well expect that this process is going to continue, and it could get even worse. So intervening and trying to find solutions to these problems early on is really important. And what we're seeing here isn't unique to glaciers. This is essentially what we call acid mine drainage in parts of the world which have been mined artificially by people. Is you know, you crushed up the rock in that situation, and the rock's got sulfides in it. Then you create acidity in the water, and in the same way, there people are creating wetlands to help remediate the water. And so it's trying to understanding this cycle, which is really important in determining what the future of water is in this region, and the future of that for local people. So thanks very much for listening.
Thank you, Jemma. A super fascinating talk. And I think what both talks really exemplified was the importance of understanding whole landscape processes and interactions for understanding, you know, water quantity and quality across the landscape.
So before we close this meeting, just a few final information about the speakers. So for information about both Debra and Jemma, you can follow the links provided here. I would also like to highlight some of the other events happening this week as part of the World Water Day celebration, which is hosted by the GW4 Water Security Alliance. So the website is provided here. So there are two events that we highlighted here for you. And also visit our Cabot Institute website, sign up for our newsletter, and follow us on Twitter. And finally, on behalf of all of us from the Cabot Institute, I'd like to thank all of you who attended and joined this meeting today. It was a great event. Thanks for all the interesting questions. I hope you had learned a bit more about water and its value. And wherever you are, have a great day or a great evening. So thank you very much.